Hello, and welcome back to Chemistry Online. We'll be talking on Dalton's atomic theory today. Dalton's atomic theory. So, John Dalton was a British school teacher who published his theory about atoms in 1808. So, his findings were based on experiments and laws of chemical combination. So, here are the theories he published. Number one, he said that matter is made up of small indivisible particles called atoms. The key word there is indivisible. That is, matter is made up of small and indivisible particles. Those particles are small and cannot be divided. That's what it means by small indivisible particles. Number two, he said that atoms can neither be created nor destroyed. Atoms can neither be created nor destroyed. And number three, atoms of the same element are identical. That is, atoms of the same element are exactly alike, but different from atoms of other elements. Of course, if you bring an atom of hydrogen from water and bring an atom of hydrogen from hydrogen gas, as long as it's an atom of hydrogen, those two atoms should look alike, right? Because they are still hydrogen. But it should be different from the atom of oxygen, another different atom. So that's his theory number three. Atoms of the same element are exactly alike, identical, but different from atoms of other elements. Then number four, atoms combine in fixed simple whole number ratios. That's when a compound is supposed to be formed, and atoms combine to form compounds in a fixed simple whole number ratios. That is theory number four. That's to say, when compounds are formed, you have, let's say, carbon dioxide, CO2. The amount of carbon atoms there is 1, and the amount of oxygen there is 2. So you see a simple number ratio, 1:2. That is theory number four, that atoms combine to form compounds in fixed simple whole number ratios. Simple whole numbers, not large whole numbers. 1:2, 1:3, 2:3. Simple numbers, but whole numbers, no fractions, no decimals. Then number five, all chemical changes result from the combination or separation of atoms. So a chemical change occurs either by combining one atom to another atom. Let's say hydrogen plus oxygen forms water, or by breaking down, dissociation, separation. Let's say CaCO3, limestone, is dissociated to CaO and CO2. That's dissociation. So chemical changes, chemical reactions occur when you combine or when you separate atoms. Those are his 5 theories. Now, understand that this Dalton's atomic theory explains the different laws of chemical combination. That is to say, law of constant composition and the law of multiple proportions. Now, how does Dalton's law explain the law of multiple proportion? Let's say if we have A and B to form more than one compound. Let's say we have an atom A and another atom B, and they combine to form more than one compound. Now, since the atoms are indivisible, combination will be in simple, ratios, because according to Dalton, the mass of atom of each element is fixed. So you're going to have 1:2, 1:3, 3:2, 2:3, like that. Like in the case of water, H2O, 1:2. Carbon monoxide, 1:1 CO, carbon dioxide 1:2 CO2, and all that. So that's how Dalton's law um, explains the law of multiple proportions. Now, these theories were published in as far back as 1808. As chemistry evolved and kept developing, there were some discoveries that tried to, alter the theories that John Dalton published. So we're going to see how we can modify Dalton's atomic theory to accept the new changes as discoveries have made. So we're looking at modification of Dalton's atomic theory. Does Dalton's atomic theory still apply today? If it applies, how has it changed to encompass the new discoveries that may, Dalton, as far back as 1808, didn't have all the discoveries, and so many things were not discovered by then to try to counter those theories. So after then, some things were discovered that would want to counter those theories. How would we then put Dalton's atomic theory to check? So that's modification of Dalton's atomic theory. Now let's remember the first theory for Dalton was that matter is made up of small, indivisible particles called atoms. Alright, we understand that matter is made up of particles called atoms. And these particles are small actually. But there is a scientist called Rutherford. You should remember Rutherford. He's the one that discovered proton, neutron, and electron. How does this affect us? He discovered that an atom is made up of proton, neutron, and electron. And you and I know that it's not possible for us to know that proton, neutron, electron are found inside an atom if we try to say that atom cannot be divided. For it to have three things inside means you can divide it and see proton, see neutron, see electron. So what does that mean to Dalton's atomic theory 1, which said that matter is made up of small indivisible particles? It now means that atoms are made up of particles and they are small, but they are not indivisible. They can be divided. So we can modify that theory to say that atoms are made up of three main particles: protons, neutrons, and electrons. I hope you understand how we modify theory number 1. Now, theory number 2 says that atom can neither be created nor destroyed. That's quite alright, but it can only work for simple reactions. The reactions that take place in your lab, the reaction that take place in your day-to-day life. It doesn't apply to nuclear reactions. If you have done or heard about radioactivity, you will discover that in radioactivity, the nucleus of the radioactive atom breaks open. It radiates. It breaks down. So it's destroyed to form a new atom and keeps breaking down, keep decaying. So in nuclear reaction, the nucleus of the atoms are destroyed. But his theory number 2 for John Dalton said that atoms cannot be created, cannot be destroyed. But now we see that in nuclear reactions, atoms can be destroyed. So we can say that, fine, Dalton's atomic theory 2 still holds, but for simple reactions. But when you come to nuclear reactions, atoms can be destroyed. Alright, so theory 3 says atoms of the same elements are identical but different from atoms of other elements. Now, the discovery of isotopes. Remember isotopes? Isotopes are like atom of an element having different mass numbers but the same atomic number. Like hydrogen exists as three isotopes, protium, deuterium, and tritium, but these three are still hydrogen. Now these three hydrogen don't look alike in mass number because the mass number are different. Okay, so the discovery of isotopes proves that atoms of the same elements are not alike in all aspects. Like I said, hydrogen has three isotopes and each of them have different number of neutrons. So even if they may look alike because they are hydrogen, in their neutron number they are not alike. Their mass number, they are not alike. So that's how we modify theory number 3. Okay, the discovery of isotopes knocked off that theory number 3 that said that atoms of the same element are identical. They are not identical when you think of it as isotopes. And theory number 4 says atoms combine in fixed simple whole number ratios to form compounds. Now, this is also not true. It's not true also for complex organic compounds. Take for instance sugar. You know, the formula for sugar or starch is C12H22O12. Those are not simple ratios. You know, C12H22O12 are not simple ratios. 12 is to 22 is to 12 are not simple ratios. So it's not true for complex organic compounds like sugar, all those your large molecules, but it can still be, can still work for simple equations like water, carbon dioxide, and the rest. So it doesn't work for complex organic compounds. All right, so his theory number 5 says all chemical changes result from combination or separation of atoms. That one still holds true because when you combine two atoms, you form something. That's a chemical reaction. And if you separate two atoms, you form something, and that's a chemical reaction. So that one still holds true. Now, what are the problems, the limitations of Dalton's atomic theory? What are the shortcomings of Dalton's atomic theory? Now, number 1, Dalton's law failed to explain the spectral lines of more complex elements. Remember something about excited states and ground states? When an electron leaves an electron leaves a higher energy orbital to a lower one, it emits light. That's a spectrum, and that shows a spectral line. Dalton's atomic theory didn't explain that for those kind of atoms. And also it failed to explain the existence of allotropes. Allotropy. That's to say, it does not account for difference in properties of the different allotropes of a compound. Take for instance, why does charcoal not look like graphite? Graphite does not look like diamond, but charcoal, graphite, and diamond are still carbon. They are carbon allotropes. Charcoal, graphite, and diamond are carbon allotropes. But why have we not seen in Dalton's law why they are not looking alike? Why are they not? Why does charcoal not look like diamond? Why does graphite not look like charcoal or diamond? And all that. So those are the limitations of Dalton's atomic theory. Thanks for listening.